All right, welcome to Principles of Clean Functional Programming. This is the Docker container where you can download the slides for later. If you're on UCB guest, you could try this IP address. This is my laptop. If you DDoS me, I might have to turn off my Wi-Fi. That's just so you don't have to download if you don't have Docker or whatever, if you want to follow along. Just some of the examples are sort of long. We won't have time to go through all of them. And that's my Twitter handle. If you want to bike shed the examples, that's always fun. So a little bit about me. I come from embedded programmer roots. I did that for 15 years. I always wanted to be an embedded software engineer since I was 10 or 11. Not only wanted to be a programmer, wanted to specifically do embedded programming. And what I didn't realize, what they don't tell you when you're 11 years old, is that that dooms you to maintaining C and C++ code forever. And so I got kind of burned out on that. And luckily, Adtran, where I work, we make these things that go on the other end of your internet connection. We have a pretty good culture of innovation. We do regular hackathons, and so I started trying to learn functional programming, sort of to alleviate my boredom. The first time I tried to learn functional programming, I utterly failed. Maybe you guys have had the similar experience. You get to monads and you sort of get stuck and give up. And the second time I tried, I got it. I understood it, but I found it utterly impractical. And the reason behind that was I didn't know how to make it readable. And I didn't know how to find code that was readable. The third time I tried with Scala. And Scala helped me with that because with Scala you have objects, and you could go look in the documentation and it tells you all the little functions that you could call on that object. And there were all these simple little functions that were really nice. These simple little functions like map and filter and reduce. And all of a sudden I could see these simple functions that I could call and use. And that helped me find other programmers that were writing readable code. And that sort of kicked me off into sort of hit the baseline of what eventually became this talk. And manager noticed that I was getting burned out on C++, and I was doing Scala in the hackathons, and he moved me to our microservices platform, which is what we use to manage a whole ton of these sort of devices. And that's written in Scala mostly, and we also do some Python. You can write Python in a very functional style if you like to. And so that's about me. Whoop, wrong button. The end. All right. Okay, so what we're going to talk about today, we're going to talk about some principles that you already know from imperative programming and how you can sort of adapt those to functional programming. And then most of the talk is going to be principles that are specific to functional programming, and that's going to be broken down further into some general principles, some principles specific to iteration, and some opportunities from immutability A lot of times when you're brand new to functional programming, writing clean code around immutability feels kind of difficult, but immutability actually opens up a lot of opportunities to make your code simpler and more clean. And we're going to talk about some ways to be able to do that. Just some general notes. These are not hard and fast rules. A lot of times when people give talks about clean code and readability, people end up repeating those as hard and fast rules. So I don't want to see these repeated on the internet as Karl said, always do this, or Karl said, never do this. These are guidelines. I want to see you help you recognize, this is why my code feels a little awkward, and give you tools that help you ask more specific questions when you go to get help. I know for me, when I was first learning functional programming, I went to ask for help on Stack Overflow or whatever, and you ask and you say, my code is not very readable, can you help me? And people have a hard time giving you help that way. But if you ask a question like, this code is using recursion and I really would like to use a higher order function instead, you will get a ton of really good help that way. So the idea behind this talk is I want to help you be able to recognize some more specific questions you can go to ask help. These examples are for readability. I tried making some more shorter, contrived examples, and the trouble with that is if you write short examples, by definition, short examples are sort of easy to read, and it's hard to see the readability problems with it. They look really fake, and so I apologize in advance. A lot of these examples are going to be interesting. You're going to want to dive into them and download them later and dig into them. Come and find me later. They're kind of interesting, but try and look at it, just squint at it, look at it from the big picture from a readability perspective instead. And this talk only shows what to do, not how. So like I said, go and ask those specific questions instead of, it's not going to show you exactly how to make the changes, but it's just guiding you into those specific questions. Okay, so this is probably, ironically, the most repeated advice on readability. Don't repeat yourself. And how it applies a little differently in functional programming is you have actually a lot more opportunities to avoid repetition. And I have an example here. This is from Stack Overflow. And you see right away this type name equals is repeated. You have this repeated assignment. And it's pretty obvious we can get rid of this var, change it to a val. And get rid of a lot of repetition there. But if you've done a lot of imperative programming, you might not think twice about the repetition of this contains label, contains label, contains label, contains label. That's something that in imperative programming you can't really eliminate that sort of repetition inside your loop conditional, or it's difficult. But in functional programming, that sort of repetition can almost always be factored out as well. So look for those opportunities. And here's an example of doing that. You could pull it out into a mat, and pulling out repeated things in if statement conditional into a data structure is a pretty common pattern you can do. So here, that contains label that was repeated 4 times. We just put it once here, and we put it a little extra error handling in there just for good measure. All right, a couple more principles from imperative programming. Don't nest excessively. So even if this is something you're used to from imperative programming, it's pretty obvious when you're nesting excessively in imperative programming. When people transition from imperative over to functional, and I had this issue myself, because functional programs are basically one large expression. When you move to functional programming, a big nest of expressions just feels more functional. It looks more functional. And so it sort of feels right. And it's also easier to write when you're in the flow. But when you go back and read it, it's really hard to read. And so it's okay when you're writing to write it that way, but go back and put a few semicolons in there. And those semicolons don't mean that it's imperative. Trust me, when you go back and substitute it all back, it's still one big expression. It's still perfectly functional. But it's easier for humans to read. So that's one thing that you need to keep in mind when you're transitioning from imperative style to functional style. And also use small functions. People are used to using small functions in imperative programming, but the idea of a small function in functional programming, a small function in functional programming is even smaller than what you would consider a small function in imperative programming. A small functional function is even a one-liner with just a couple words. So if you're having trouble getting something to type check, if I'm having trouble getting something to type check and I notice it's really big, I will always try and just grab it, split it up, and that will often solve the problem for me. So here's an example in JavaScript. JavaScript in a functional style is getting a lot more popular. I talked to quite a few people at meal times who are doing JavaScript. So I thought I'd throw a couple JavaScript examples in here. So you can see this guy was trying to learn JavaScript in a functional style. And so he used a lot of nesting here. He has one sort of really big function. And it's sort of hard to tell what's going on, what he's trying to accomplish here. And if you break it up, you could give some names to those intermediate values here. You can see this function is a pretty small one-liner. And even though you don't really know what this is doing, it's just easier on the eyes, I think. All right, so before we move on to principles specific to functional programming, any questions on what I've covered so far? Okay. All right, so we hear this a lot. Isolate I/O. And in Haskell, this is even enforced on you by the language, by the I/O monad. But even when you're doing functional programming or programming in a functional style in other languages, even in your imperative languages, your Python or your JavaScript, or even in your day job languages, your C++ or whatever, keeping your I/O in as small a box as possible and making as many of your functions pure can really help your code. And it bothered me. The people always say this is because pure functions are easier to reason about. And I never really knew what that meant, the reason about. And so I thought I would lay that out for you guys here. This means that pure functions are easier to reorder. They're easier to refactor. They're easier to run in parallel. They're easier to type check. They're easier to share data between themselves. They're easier to test, and they're easier to compose. And so here's an example of a function that converts a decimal number to a Roman numeral. And this is the before example. This is a function that I wrote myself. And you can see it has a return type of unit. It has a print line here as a base case. It prints one digit at a time. And this suffers from a lot of those problems that I listed on the previous slide. You could just print one Roman numeral at a time. If you want to do anything else with it, like send it over a network, do it as part of a sentence, things like that, you're going to have to modify this function in order to, or create another function in order to get things done with this. But if you make this function pure and return a string, this part is pretty much the same complexity, but then we can make the previous version of the function the same, just with composition, and we can do whatever we want with the previous function. We don't have to modify this function at all in order to use that function in different applications. And so because we can, it's basically this function can stay stable and doesn't need to change. And so we're less likely to introduce bugs in the future. Okay, don't try to eliminate all intermediate variables. So here's another question posted to Stack Overflow. This guy was looking for help to eliminate this var here. He wanted to make this function pure. And you can see he has this val metadata here that I don't know what it means, but it had some meaning to the original author of the function. He just didn't know how to get rid of this var that he was updating with this append in this for loop. And the accepted answer on this function was this one. So you guys are laughing. So I guess I was right that, yes, it's a pure function. It's very functional, but you can see that metadata went away, and we all in the room didn't know what that metadata did, but we have no idea. We lost a lot of human readable meaning in there. And this function here, it looks more functional, but we lost a lot of human readable meaning here. And we can still retain that metadata and still retain the pureness at the same time. There's nothing wrong with splitting it up, having two separate blocks of computation, there's no problem with that. It's still perfectly functional. The functional police aren't going to come and take your license away because you put a little white space in there. All right, so this is the one that I thought might be a little controversial. So when people first learn about pattern matching, it's this new syntax and people love it. And they put it everywhere. And pattern matching is great. It can simplify a lot of code, and it has its uses when used appropriately. But there are a lot of places where it is not appropriate to use, and it can actually add bulk to your code. And the reason why you don't want to use it in a lot of cases is because it's overly general. There are a lot more specific tools that are already available. It's verbose and repetitive. You do get the exhaustive checking for some types, but there are other kinds of mistakes you can make that the type checker can miss. And you're often reinventing the wheel. That type might already have a function available that you're reinventing. I see sometimes people, for example, on an option, they might be doing pattern matching on an option where they could do something like a get or else that will accomplish the same thing. So that being said, there are lots of good times when to use pattern matching. Probably the best time is when you need exhaustive matching on a sum type that you created yourself. This will give you a compile error when you forget to handle one of the cases. So I'm not saying never use pattern matching. I'm saying use it when you want that compile error. When you're extracting values on the left side, especially when there are lots of nesting complex conditions that you're using on the right side over here. When there aren't existing more tailored functions that fit better, like that get or else on an option. And when you've written it both ways and you've found it cleaner. So I've had times where I try really hard, I say, I think I should be able to do this without pattern matching. And I try to write it without, and the pattern matching just looks better. And so I do it with pattern matching. So here's that Roman numeral example again, written with pattern matching. And so, you first think, I have a whole list of Roman numerals that I want to match against. You can see we already saw the example, but you can see why it's sort of inappropriate. This repetition here, case f x of x, case f x of... All right. Time for some water. That's repeated. The 1,000, 1,000, 900, 900. We got a lot of repetition here. And so this sort of falls under also the don't repeat yourself rule as well. And if we show the finished version again. So sometimes I think I need to match against a list of things that's pattern matching. But matching against a list, I want you to think a list. So that's why I put this into a list and then matched against the list down here. And remember, in functional programming, everything is a value. And putting things into values and working with them as values is one of the great strengths of functional programming. And looking for opportunities to do that can a lot of times, most of the time even, simplify code that in imperative programming you have to write out structures like pattern matching like case statements, whatever, to accomplish. Okay, don't overuse lambdas. So this is another example that people get a new kind of syntax and they want to use it a lot. At first they don't know how to use it, so they try it almost to extremes. And it's fun and new and exciting. And back to that JavaScript example, he was trying to learn JavaScript in a functional style. And so that, in his mind, was use lambdas for everything. And you see even down here, there's lambdas of lambdas. And I don't mean to rag on this example. When you're learning as a learning tool, it's often useful to take something to the extreme. And I kind of call this similar to a lens focus. When you focus a lens, not like a lens as in the lens that we've been learning about, but a camera lens. When you try and focus a lens, a camera lens, if you take it past its focusing point and then back, it's often easier to see the right value. So when you're learning, if you take something too far and then back, it can be easier to see the right value. And so I think this guy, if you look at his actual thing, he learned that taking it too far and back, he got good practice and then backed it off, and this was a good learning experience. But my rule of thumb for lambdas is if you could think of a good name for them, then give it a good name. Go ahead and pull it out to a named function. But if your name for the function would be something like index of is not equal to 1, then that's a lambda, because your function name would be the same as your expression name. So that's my rule of thumb. It doesn't always hold. Often things like callbacks or things that might be a little longer lambda. There's exceptions to rules. But that's my rule of thumb as a starting point. All right. Don't jump out and back into monads. So I promised this was going to be a very beginner level course or talk. You don't need to know what a monad is. By that, I just mean types like options and lists and features. So what I mean by jumping out and back into is, say you have a string, an option of a string, and you want to convert it to an integer and then put that back into an option of an int to see whether that actually succeeded or not. So what I mean by jumping out of that monad and back, here we extract that value, we handle the case of none and none, and then we do this conversion, put it back into the monad. And the way you avoid jumping out and back in is by using either a for comprehension or a flat map or a map. And the standard library types especially handle that well. So here you can see that it simplifies your code. You don't have to handle the none case, especially if you have a lot of these. You're doing an option, then you have a feature, then you have a list or whatever. It can really simplify your code to not have to jump out and back in and out and back in. You just chain these flat maps or do it in a for comprehension or things like that. Okay, on to iteration. Okay, this one tripped me up a lot that second time that I gave functional programming a try, and I thought it was really impractical. So don't say this out loud, but fill it in your head. Functional programming doesn't have imperative loops, so instead we usually use, most people, I think, put in recursion here. And I actually went through one of our microservices at work, one of our Scala microservices, and I was curious as to the ratio of recursion to higher order functions that we used. And we actually used recursion 0 times in that microservice. And I was surprised. We have some libraries that are more functional, the monad libraries that are sort of the low-level libraries that use recursion more often. But our sort of high-level libraries that we use that our production code is, we almost never use recursion. And the readable code, the day-to-day code, you should try to use higher order functions if at all possible. And the reason is, there's a number of reasons. First, recursion is harder to reason about. It's overly general. It could be applied to any situation. And I think this is why people like to reach for it. You can always use it. Whereas higher order functions, you have to go and search for the function. If you don't know the function on top of your head, you have to go and search for it. You have to go and ask for help if you don't know the function already. It's easy to accidentally overflow the stack if you don't know what you're doing, if you're not careful to make it tail recursive, if you don't know how deep your stack actually goes. It's easy to make your functions too large. Remember earlier I said your functions, making your functions too large makes it easier to, makes it harder to get it to type check. And it's easier to make mistakes that the type checker can't catch. When you already have higher order functions that have very precise type semantics, you get a lot more help that your type checker will help you with, that people have already debugged these functions for you, and you have a lot less work that you have to do yourself. And you're often reinventing the wheel. I've seen people on Stack Overflow write recursive functions that basically do a filter, or a filter in combination with something, and you're just making it harder on yourself. That being said, there are obviously opportunities when you should use recursion. Like I've said before, when you've written it both ways and you found recursion to be cleaner. When the stop condition is complex. So you may not know exactly when you start how many iterations it has to go through, or it may be really hard to tell when you need to stop. And those are really hard to write in a non-recursive way usually. When you would typically use recursion in imperative programming. So a lot of functions are easier to write in an imperative style in recursion. And usually if you would have written it recursively in imperative programming, you also want to do that in a functional programming. When the call stack manages data that you would otherwise have to manage manually. So this is, when you write it both ways, you'll see that on the non-recursive side, extra variables will pop up that you have to manage. And that's a good sign that you should just use the recursive version. And it's often beneficial to use recursion to create a new higher order function. So don't say, well, I have to use recursion, so I'll just use recursion for everything. Try and limit the recursion to a small part, and then make that a higher order function, and then call the rest call the rest of the code, just like your I/O, try and limit the amount of your code that's recursive. And so here's a version of that Roman numeral example again that is not using recursion. And you can see here we have a couple of extra variables that pop up. This Roman digit, decimal digit, and we have also this extra bit of logic that we have to handle. And it becomes a lot more things to keep track of when we write it in the non-recursive version. And so that's why I elected to go with the recursive version on this one. So it's often a good exercise to just try and write it both ways, just to see how it works out. And it's usually possible, but try and avoid recursion when it makes sense. Okay, don't use loop indices unless they are referenced directly by the problem statement. So in imperative programming, we do a lot of things. We will have a nested loop where we have a loop index like this LNR here that keeps track of your position in a loop. And the reason why this often complicates functional programming is because we're using pure functions. And so in pure functions, all your data has to be passed in as in the arguments. So you not only have to pass your array, but you have to pass in the loop indices as both your function outputs and your function inputs. And where in imperative programming, in an imperative loop, you don't have to pass that. So if you're passing your loop indexes as well as your arrays, you're passing in 3 times as much data, basically. And so this makes your functions a lot more complicated when you try and port them over to a functional style. So this version, we use a vector instead of an array because a vector can do either an init or a last in O1 time. And then we just make a stream of those. And then we could check for the target condition. And here we don't have to pass that LNR from the previous version. So this guy was looking to get rid of that LNR vars here. And if we had tried to do it, we would have had a lot more than just this one value that we would have had to keep track of, this one array, or this one vector. All right, so look for opportunities to factor out loop structures. So I went to an excellent talk yesterday on recursion schemes. That's one sort of advanced way I would consider to factor out loop structures. There are lots of different ways in functional programming that you can get rid of your loop structures. So here's an example of someone looking to make his tree traversal finding a node in a tree simpler. And here's one way you could solve that. You could separate out the traversal by producing a stream of tree nodes. And then you can use that traversal in a number of different operations. So this is just a stream find and looking for a specific node. You can also reuse this to say, sum all the nodes, or average all the nodes, or I don't know, do any number of operations. So this function was not terribly easy to write, but you only have to write it once. And then everything else is very simple to do. So you can separate out the loop, whereas in an imperative style, you sort of have to always tangle your loop code with your loop checking code. Okay, so opportunities from immutability. So keep relationships between objects outside of the objects themselves. So when we have mutable objects, we often, so if we were keeping, say, this is an example of a dungeon where we have a number of rooms and we have a room to each direction with, a description, some monsters, some loot. And in an imperative style, we would keep it like this, maybe, where we have everything in one object. This is an example of a recursive data structure. And there are ways, there are lenses, there are recursion schemes, things that can help you do this. But if you assign a grid and put this in a map, this is a lot easier to update. You can do this incrementally. You can use simpler techniques. You don't have to know about recursion schemes and lenses. You can just use regular map updates. And the beginners on your team can understand it without having to go into all these deep techniques. Those deep techniques are fun and they're useful when you need to go there, but oftentimes you don't need to go there. And also, because of immutability, you can use small flexible data structures and transform them on demand. So an example of this, from when you have mutability, you often want to keep all your data together so that when one reference changes, you know that everything is synced up still. If you have forward references between, say, a game square and the node, you also want to make sure that you update the reverse references between the game square and the node at the same time, and the occupied squares at the same time, and the list of all the nodes at the same time, so that you don't lose sync between those two. And we sort of get this fear when you work with mutable code that your references will all get out of sync with each other. But with immutability, you don't have to have that kind of fear, because you control when you get the updated references. And here's an example. You can just have this board that's a map from, say, night 1 or whatever to the node. And then as you go through your reference code, you can take the board and just get the key set. And you know that this stays in sync with the board because they're immutable. And you know when in your game loop when that updates. So you don't have to keep these in the same larger data structure. You don't have to be afraid that somewhere halfway through your algorithm that this occupied squares is going to be different than the square in this board. And then you can go later on and say, I want to know all the squares that are in this row and all the squares that are in this column. And you don't have to be afraid that this is going to be out of sync with this occupied squares. And that's because of immutability. You don't have to have this kind of fear and keep everything glommed into one large data structure. So learn to not be afraid that your code is going to change out from under you. So we've talked about some principles you already know from imperative programming and how you can apply those or extend those to functional programming. We've talked about principles specific to functional programming some general ones, some ones about iteration, and some ways that immutability can help you not be afraid to change your code and keep it in sync. Any questions? Okay, thank you.